Today we are going to be going over flexible combiners. This may be a couple part episode. It's definitely going to be more than one. So this first episode, I'm going to be going over definitions, how to navigate the combiner, and some basic stuff. But the majority of this, we're going to spend on the definitions because until you know what all these definitions are, you're going to struggle with this. So what is a flexible combiner? A flexible combiner is the E2 and Emerson's open logic, meaning you could do custom logic. That is their version of custom logic. So it is Boolean line logic is what it's called. So you're using Boolean math problems and logic statements in order to make custom logic. Now, this is much more difficult than doing block logic. So block logic is a lot easier because it's on the screen and it's, visual. You can see what you're doing wrong. Line logic is more difficult. I find it to be easier now. I mean, I've been doing it for a long time, but the majority of guys, don't ever need to even get into this. This is all custom stuff, like one-off stuff, or you're trying to do some custom programming inside the E2 that you need this flexible combiner to do custom logic. Now, with that being said, guys, once these are set up and they're working properly, there's no need to be able to get into them and really mess with them. You may need to troubleshoot it a little bit, how to look at some inputs and outputs and some graphs on there. But for the most part, if the logic is solid, you shouldn't have any problems where you need to get into these flexible combiners. I think it's more of a thing that guys, mess with and mess up more than they need to. So a flexible combiner. This is right here is a good application of it. So you have analog inputs, digital inputs, and analog outputs, digital outputs. So you have analog inputs coming in and digital inputs coming in and making statements, and analogs and digitals coming out. So in this example, so they have AO1, meaning so this is AO1 output, is AI1 plus AI7 divided by 2. So AI1 plus AI7 divided by 2, and that equation is going to be AO1. That's going to be the value for AO1. This is DO2. So it's DO2 and DI1 through, I can't really see, or DI3, or through DI3. So if any of those comes on, it's going to bring on DO1. So we're taking inputs and outputs and making custom logic, okay? So you are limited to up to 80 characters for each equation. So you have 2 lines. Generally, it's 1 line, and you can make it 2 lines. So I'll show you on the inside the flexible application once we get that far. But if we scroll down here, so you have a couple things here. You have inputs, outputs, and analog inputs and outputs. This will probably be easier to show on the computer. Let's go over the definitions first. I think it'll be easier to do this and then show you on the E2. Okay, so this is the engineering units. So you have temperature, you have Celsius and Fahrenheit, you have change in temperature, which is delta temperature. So that applies the change before the math is made. So DDF, DDC. You have pressure, you have change in pressure, which is delta P. You have air velocity, you have liquid velocity, you have volume flow. So these are your engineering units you're going to change. Now, selecting the correct engineering units greatly affects things. So the way, if you read this up here, so of all the equations, AI1 plus 10 would be incorrect because it would add 10 to the value of AI1 in Celsius, since the E2 SI units for temperature is in Celsius. So it does all the math in Celsius. So if you want to do AI1 plus 10, the correct way to do this would be to convert the number 10 to the equivalent value in Celsius. So AI1 plus 5.6, or use the correct suffix in the E2. So if you want to add 10 degrees to AI1, so it'd be AI1 plus 10 degrees DDF. So that's where this DDF, this change in temperature, comes in, because now it's going to add to that before it does the math in the E2. As you play with these, you'll notice like your values will be way off, and that's when you need to use the DDF. Okay, so you have electrical current amperage, power rate in watts, power consumption in watts hours. You have illumination. You have integers, non-integers. So as you go through all these, I mean, a lot of what you're going to be doing is temperature, pressure, stuff like that, and we'll go through some other stuff. So now you have constants. So pi, which would be 3.14. I've never used this. A couple things. So true and false. So everything inside these combiners and in this logic is equal to 1 or 0. So 1 is equal to on, 0 is equal to off. Okay, true is equal to 1, false is equal to is 0. So if you look on here, you have true is 1, on is 1. So it's all ones and zeros. So that's part of Boolean logic. So when it's on, it's 1. It's true. The statement is true, or the relay is true, and it's on. If it's off, it's false, it's 0. So that's one thing you guys got to like get in your head. Like there's multiple different ways to write these equations. That's why it's kind of difficult to troubleshoot them if you did not write them, and if you didn't write a sequence of operations with them. That's one thing that I even struggle with. I don't do it a lot of times. Writing a sequence of operation of how the flexible combiner works. You could build the best flexible combiner in the world, but if nobody else can read it but you, it's not a good combiner. So, I mean, I see guys get really complicated with this stuff, and they're just, their whole thing is nobody should have to ever mess with it. So, here's some more suffixes down here. So you have GPM, gallons per minute. So you have liters for L, CFM, CMS, amps, milliamps, percent. That's one that gets used a lot. Cubic feet, feet. I mean, I seen some pretty cool GPMs that another guy I know was doing. He was doing some like pump calculations with GPM. It was pretty cool. Not gonna lie, the math is way over my head. Not sure how he came up with all the pump curves, but somebody way smarter than me came up with all that math. So a lot of these flexible combiners, like I will make them and save them. So like I have ones for pumps that I've made and tested. I have ones for condenser stuff that I've made and tested. After you make them and test them, I take screenshots of them and I save them. So like whenever I'm doing another one, I could easily, okay, boom, I'm going to add this flexible combiner in. I already know what all the logic is. I can just copy and paste everything. So that way I don't have to do that and assign my inputs. It makes like when you're programming a lot easier. So like I have a library of flexible combiners that I've spent a lot of time making that I keep on my computer. Okay, so these are all constants. So again, this is more of the suffixes. So like DDF, delta degrees Fahrenheit, used as a suffix for offsets. You got KW, RPMs. So like there's hundreds of different engineering types in here. So we're going to skip through all this, and I want to get to what they call the operators. So this is what you use to make the equations. So you have the plus sign, adds 2 values. You have the subtraction sign, it subtracts 2 values. You have the multiplication sign, it multiplies values. You have the division sign, same thing, it divides values. You have the exponential. The value on the left is raised to the power of the value on the right. Never use that. The equal sign. So equal comparison of 2 values. So result is 1 if the 2 values are equal and 0 if they're not. Never really use that, but it is what it is. Inequality, comparison of two values results in 1 if the values are not equal and 0 if the values are not equal. Greater than. This is where it comes in, like greater than, the less than, the greater than equal sign. Use those a ton. So greater than comparison of two values results in 1 if the left of the sign is greater than the value to the right of the sign. So if 4 is greater than 2, it's 1. So it's true, it's on. So that equation would be true. So if 4 is greater than 2, it's going to be on. Okay, so if 4 is greater than 3 plus 1, it's not. So 3 plus 1 is 4, so it's not greater than. It'd be off. It's false. It's 0. So like less than, same thing on there. So if you go down to here, now you have greater than or equal. So like that same equation, so is 4 greater than or equal to 3 plus 1? No, it's not. It is. It's greater than or equal because it's equal. 3 plus 1 is 4, so it's equal. So greater than or equal, same thing with less than. Okay, the exclamation point. It's a digital inversion of the value to the right of the sign. If the value is non-zero, the result is 0. If the value is 0, the result is 1. So digital inversion of 0 results in 1. Digital inversion of 7 is now 0. So this value is non-zero, so it's 1. This value is above 0, so it's digitally inverted to 0. Okay, the not. Same as using the digital inversion, but a different format. So, but it must be in parentheses. So not 0 equals 1, not 7 equals 0. So same thing, just a different way to write it. Okay, now we have the AND logic. This is something we use a whole lot. So logical AND, if the values to the right and left of the symbols are both non-zero, it's going to be true, false. Or it's going to be true, it's going to be 1. So 4 and 2, they're both non-zero, so that's 1. So 4 and 0, it's going to be 0 because one of the values is 0. So 0 and 0 is going to be 0. It's still true. Or still false. So logical OR, this is something we use a ton. So logical OR, if either value to the left or the right of the symbols are non-zero, the result will be 1. If they're both 0, it'll be 0. So 4 or 2 is true, it's 1. 4 or 0 is 1 because one of the values, it's OR. So 4 or 0, one of them is not 0, so it's still going to be 1. 0 or 0, that is 0 because both values are 0. So this is where we start building equations off these. So you have your constants and you have your operators. Your operators are what you're using to build equations. So this is where it starts getting complicated, where you start having to put parentheses. And functions. So equations for most applications are being built using nothing but inputs, constants, and operators. However, some cases, it's not always physically easy to use nothing but components. In some of these cases, you would need to exceed the 80 character limit. So this is where we start using functions. So functions are always evaluated first in the equation from left to right, unless parentheses are used. So when you start adding these parentheses, you can change where the math is done first, just like you would in algebra. So this is where functions come in. So MOD number divider divides numbers by the divisor and returns the modulo of the remainder division operator. An example, mod 16.5, the modulo 1, because 5 goes into 16 3 times with a remainder of 1. Never ever use that. So you have ABS number, you have fraction value, you have inter value, you have ceiling, floor, you have truths, you have round. A lot of these, like, I never even use. Like, we never have to use these. This is one I use a lot, scale. Okay, scale returns a number between low 2 and high 2 that is linearly proportional to the value regarding to low 1 and high 1. Note the value, if the value is outside the range of low one and high one, a bad value is generated. So a bad value would be a error message saying the equation is false. So scale 5, 10, 0, 3 results in 1 and 5. So it's going to range between 5 and 0, and then the other range is 0 and 3. So between 0 and 3 it's 1.5. So that is scale. We use this for floating limits. We could use this for circuit controls. We could use it for ambient air fake outs. We could use it for floating ambient temperatures. So then you have limit value. So this is pretty close to scale. Limits the high and low possible values of a number. If the value is above the high number in this limit, the results will be equal to the high number if the value is below the low number. So as you can see in here, we use this value a lot. Range, another one that gets used on occasion. So we'll put this document up, guys, and you can look at this. I mean, I reference this document the entire time I'm writing these flexible combiners. You know, it's a lot of help. So if you look on here, you have median, you have max, you have minimum range, you have average. So you could average sensors. So like average 2, 5, 7, 14 results in 7. That's the average of all those. So you could average AI1 or AI11 through AI17. That's going to average those sensors. So this is where the meat and potatoes come in. So cut in, cut out. So cut in, cut outs are like great examples of almost like a sensor control. So returns a 1 or a 0 based on the following. If test is below the low, the result would be 0. If test is above the high, it'll be 1. If test is between the value of low and high, the result may be equal to between. Should be filled out by the name of some output in the building the equation you're building. So cut in for this first example is -5, 5, 12, and DO1 results in 0 with low. So the value is -5, the set point, the cut in is 5, the cut out is 12, so it's 0. It's below the cut in. Okay, cut in 14, 5, 12. So the cut in is 12. It's 14, so it's above that. It's high, so it's going to be 1. So if you look on here, cut in 7. The value is 7.5. The cut in is 12. The cut out is 5. It's going to result in DL1 being in between. So if it already cut in, it's not going to cut back out until it gets below 5. So cut in, cut outs, we use these a lot for fans. You could use these for anything you need to turn a relay on. So count, you could count this. This is good for like if you're trying to count the number of cycles on something, or the number of times the oil valve pulsed, or the number of times the separator feeds. I do this a lot for like separators, where I put a sensor on the outlet temp of the separator. I'll count the number of oil feeds in an hour, and I'll have it log it, so that way I can see how many times an oil separator is feeding an hour. Vote and range. This gets used on occasion. I'm not going to go over that. So So returns a 1 when all the values in a range are non-zero. This gets used a lot. So and 1 and 1 is 1. And 0 and 1 is 0. So both of these values have to be 1 or true or on for it to result in a 1. So or. This gets used a ton. So or is the opposite of and. So or is if one of the values is on, it's going to return a 1 or true or on. If one of the values is off and one value is on, it's still going to do that. If both values are off, it's going to return a 0. If both values are on or true or 1, it's going to return a 1. So or is the opposite of and. So XOR is the same as or, except returns a 0 when all values are non-zero. So if both values were 1, if both values were on, it's going to be off. So it's the opposite of or. I know this is kind of super boring in the beginning, but like we got to get through some of these, before we start writing these equations, because otherwise you guys are going to be like super lost. Square root stuff, not a lot of stuff we use. All right, so logged in V2. I already have some flexible combiners in here, um, some ones I made, but we're going to add a new one. Then we'll kind of go over those. So add new application. We're going to call it. No, there's already one called test 1. We'll call it test 2. Okay, application made. Go to test 2. We're going to go to edit application. Okay, so first page, you're going to have your name. You're going to have your long name. You're going to have your update rate. So first things first, if you don't have a flexible combiner that requires like things to happen quickly, if it's just like slow logic, you can leave it at 20 seconds. But for testing purposes only, I always drop it down to 2 seconds. So when you're testing it, you don't have to wait 20 seconds every time you make an input change. If you do have a fast-acting flexible combiner, like if it's doing fan logic, if it's doing basically anything, most of my stuff gets dropped down to 2 seconds, which is the lowest you can go. So number of analog inputs. So you could change this to 8. Okay, if you have no analog inputs, put it to 0. Number of analog outputs, you could have 4. So if you have no analog outputs, put it to 0. So we'll start with 1. Number of digital inputs. If you have none, put it to 0. If you have up to 8. Number of DOs. You could have up to 8. Number of alarms. You could have up to 4. So analog memories. You could have up to 4. That is an AO, but it remembers where it was at. So if the controller were to power cycle or anything like that, it's going to start out on that analog memory. So show equation line 2. So if we go to the equation lines, this is where all of our stuff's going to be. So notice we only have AO1, AO2, or DO1, DO2, DO3, DO4. So if you go back to this general screen, you click yes, equation line. So now you have AO1 and you have AO1 equation line 2. So if you run out of room on AO1, the first equation line, now you could have the second one. I generally don't enable this unless I need to because it just makes it more confusing. So DO1 type, you can have digital or one shot. A one shot is just a pulse. So DO2, same thing. We'll put this one to a one shot. Okay, and then trigger is edge, NV edge or bolt edge. So this is how we went over that thing. So one is triggers the output when it switches from off to on. One triggers the output when it switches from on to off. One triggers the output, the reverse. So we'll just put it to edge. So now we go to inputs. This is where you assign your inputs. So on this, so you could either do a fixed value. So if you have a constant, meaning like a constant temperature set point. So we'll say 20 or 22. Because I fat fingered that. And I just lost connection. Okay, so we go to inputs, back to inputs. Say we want to make this a constant. So fixed value. So this would be a constant, 20. Okay, we could assign inputs here 2 ways. You could assign pointers, so you can grab things from all these applications, or you could assign board points here. Same with DIs. DIs are the same way. You could do constants, so you can put a fixed value of on or off, and then or you could do a pointer. Okay, or you could do an board point. So you could do all those. This is where you're going to add your fixed values, your constants, all that stuff. So outputs. This is where you're going to assign your outputs. So AO1, whatever that output is going to, your DO, AO2, DO1, whatever that is triggering. That could be a board point. It could be another application. So you assign it here. You could assign this to a board point. You could assign it to a pointer. So you can make it do different things. So then you have your DO1 delay on. Same thing. You could assign that to a board point or a pointer. If you had an AOM, so if you did an AOM with the output, so now we have AIM1. Same thing. You could assign this to a board point. So an analog output or a sensor or control or an application in the E2. So now we have our output equations. So this is where all of our output equations are going to be. Inside of this boxes, this is where we're going to do all of our math. And then delay pulse width equations. So this is where you would do your on delays and your off delay equations. Engineering units. This is one that is super important. So this is where you choose your engineering units for your inputs and outputs. So if these are not correct, they will mess up all your math. So, I mean, it takes a little bit of playing with it. So, like, see how these are UI1? So these are just going to be a nominal value. If these engineering units are not correct, then nothing in your math will line up right. So the biggest thing for me that took the longest was getting the DDF and DF right. So defrost Fahrenheit and delta defrost Fahrenheit. That was the hardest thing for me to get through my head of when I need to use it and when I don't. So not really using this in this equation error screen, not a big one for me. Description. Please fill this out. This is extremely helpful when you're troubleshooting this. So this would be main. Okay, then say this is temp. This is fan. So you want to name these as descriptive as you can. So you get up to 24 length characters. So try to make it as descriptive as you can. So input output status. This is where you're going to see all your stuff. So okay, this is where it's giving you your analog out one. Okay, we didn't apply this, so I'll apply real quick so it pops up. Okay, so AO1, it'll give you your engineering units, AO2 engineering units, its percentage, the analog status, it's okay. So AO1 equation error, there's no equation. So it's giving us that equation error because we have no equation made yet. So it tells you your on delays for your relays, your off delays for your relays here, and then it's giving you the equation errors down here. So we have no equations. So we've done nothing with it yet. So we hit okay. Now we go into this graphical status. This is where it's easier to test. So in here, we have our analog inputs 1 through 8. We have our analog outputs 1 through 4. We have our digital inputs 1 through 8, if they're there. And then we have our digital outputs 1 through 8. So I'm glad it used to be only 4, now they upped it to 8. So right now, this is if you want to override this. So if we went to override, yes, we could override the test. You cannot override analog outputs or digital outputs to try to test. It won't function properly. You have to override the analog inputs and digital inputs in order to make the test happen or the fixed values. So if we go out of here, I'll show you this round robin one I made. So this is basically taking a average box temp and it's switching units around. So this is like a lead lag setup. So A1 call, A2 call, A3 call. So you got 3 evaporators in here, and we're enabling and disabling the evaporator or the condensing units based on time and so this is my equation for DO1. If DO1, I'm sorry, DI1 plus DI2 plus DI3 equals 2, it's going to be on. If not, it's going to be off. So if DI1 plus DI2 plus DI3, say it equals 3, it's going to be 0. Say it equals 1, it's going to be 0. And then DO2, if AI1 is greater than or less than 36 degrees, on. If it's not, off. Or new day. So if the temperature, I'm sorry, gets greater than 36 degrees, it's going to turn on. If it's not, it's going to be off. Or new day, meaning if the day switches, it's going to switch. This is like a basic one. I think we were there was still some stuff to do on this. I mean, I was just testing it on here, but this is how we. Okay, guys, so let's go back into our test. Edit application. So we're going to do a quick cut in, cut out. So cut in, out. So we'll reference this real quick. Don't use cut in, cut out a whole lot. So right here. So cut in and out. So this is how you got to write it. So cut in, out. So bring back up AlterSite. I try to do everything with caps lock on. So we're going to make, the first is going to be your operator. So whatever your, so we're going to make it AI2. You know, what did this do here? There it goes. So, oh, there it goes. So we're going to make it AI2. Okay, then the next is going to be your cutout set point. So we'll go 65 DF, comma, then we'll go 72 DF, comma, then it's going to be DO1. Okay, so the way this is, so AI2 is going to be your input for this application. 65 degrees is one of your set points. 72 degrees is one of your set points. And then it's operating DO1. You have to tell it what it is. So we hit apply. So if you go to here, DO1 equation is error none. Okay, so AI2 is 67 degrees. So if we go down here, DO1 is currently off. So if we raise this to override it, we'll override it to 75 degrees. DO1 just turned on because we are above 72 degrees. So it's cut out, cut in, operator. So if we go back down here and we lower this to 64 degrees to our input output screen, if we lower this to 64, it just switched it off. Because if you look, the equation reads cut in, cut out, AI2, which is our operator, 65 degrees is our cutout, 72 degrees is our cut in. So it's always backwards. So it's going to be your cutout, cut in, operator. So that is a basic cut in, cut out. Now, so that is how you do a basic cut in, cut out. So we'll take this out. So we tested that. That works properly. Take the override out. So back to 67. Not really sure why that's in yellow. I mean, this E2 has been pretty taxed because I've been doing a ton of programming on it. So we'll delete this equation. So now we'll do an and equation. So we'll say di1 and, so we'll do the and equation, di2. So I have to change this. So I do have two di's. And then we'll add the input because I need the input. So we'll just make it on. Okay, we'll hit apply. So we'll go to input output status. So see DO1 equation error, none. Okay, DI1 is off. Now if we turn this DI1, override it. Remember I put a static in there, so we're going to make this on. It turned on. Okay, because the equation reads DI1 and DI2. So DI2, I put a static value of on, so it's on. So they're both on, and it's on. So if I go through here and I override DI1 to off, take the override out, see DO1 switched off. Now if we were to switch this to OR, so OR would be the two straight lines, so two dashes. So we switch this to OR. We go in here. So remember DI2 is on right now because it's a static value. Okay, so look, DI1 is off. It is off. It is on right now because DI1 is on. So if we were to take this and we overrode it on, see how no change? Now if we were to take this, we overrode it off, no change. Now we're going to take this one and override it off. See, it turned off. Can't really see it here because it's not displaying the value properly, but we overrode it, so it's in override, so it's off. So if both values are off, it's going to be off. If both are on, it's going to be on. So that's good for doing like switches, defrost termination. So let's go over a quick, we'll do an if statement. So if, this is like the meat and potatoes of what I do. It's really easy to do these to a point, but it also makes me struggle with block logic because I think if statements are super easy when I would have to do 4 or 5 blocks when I could just write an if statement. It's more fluid for me to write an if statement. So if AI1 is, so if we pull this up and you look through here, so these are what makes it easy to do. So you have your operators. So greater than, less than, this is what we're going to use a lot. So if AI1 is less than AI2, then comma, it's going to be on, comma, off, comma, apply. So if we go to our output equation, so look here, DO1 equation error none. Okay, DO1 is on. So the way this is written, if AI1 is less than AI2, so if we go back here, so AI1 is 20 degrees Fahrenheit, AI2 is 67. So 20 is less than 67, so it's on. So if we were to override this to, let's say, 68 degrees, see how it turned off? Because 68 degrees is greater than 67 degrees. So the equation is now false. So if we take this back out of override, and we go back to our equation. So this is how you could write more in here, and you can get much fancier with it. Like we'll go over some more advanced ones, but then we'll go over the analogs real quick. So say you wanted to write an analog equation that mirrored like the split fans. So we just had this on a job where we had two different condensers for split, and we needed to shut the fans off when it was in full or split. We needed to have them match the signal in full running. So the way we did this, if di1 it was going to be ai2 comma I'm sorry, it's going to be 0 comma ai1 comma. So hit apply. So if di1 is on, it's going to be 0 for the analog output for AO1. If di1 is not on, it's going to be ai1. So ai1 would be, we'll call ai1 fan speed. We'll call AO1 fan speed. Hit apply. Okay, so we go to our input output status. So AO1 equation none, error none. So if we look here, AO1 is 20. So DI1 is off, so it is whatever AI1 is. So if we were to switch this, let's say this is the split command. So when it's in split, split kicks on. Okay. Oop. Now AO1, I have it set to 0. So this is guys, this is where the engineering units comes in big. Okay, so AI1, we'll say, we'll change this to percent. So PCT and AO1 will do the same thing. PCT, apply. So see how that was 32 before. That was our error there. Okay, so now AO1. I don't know why it's reading me. I'll click on this and go back in. So we changed that PCT. It messed up our input. So we'll change this back to 20. Okay, so DI1 is on. Fan speed is calling for 20%. But so DI1 is split in this application. This is reading 0. So it's in split, it's 0%. So if we were to take this DI1 and override it back off, now this is going to mirror AI1. So it's going to bring on AI1 as the input. So if we raise this up, so we put this to 30%, it's going to match it. But if DI1 turns back on for split, it's going to shut it off. This is where you'd want the update rate like super fast, and you would want it set up that way, so that way you could you don't chase the other side of the condenser. I just had a EMS company do this to me where they had it at 20 seconds, and you had a 20-second delay between everything. So that is an issue where you need to have it very quick acting. So that's a couple like really basic ones, guys. We'll go over some more advanced ones, as we go through this. I just wanted to kind of give you guys an overhead of like how this works, like a 360-degree view of how this works. So as we get more involved with this, I'll make some like more involved flexible combiners. But like this is the biggest thing here is testing these and looking at them. And then I'm gonna make an error real quick so you guys can see it. So if we go to edit application and we go to our output equations, so say I'm missing a parentheses. So I hit apply. So see, I don't have this parentheses over here. Now watch what happens when I hit apply and I go to this. So DO1 equation, missing mismatch parentheses. So it's saying I'm missing a parentheses or it's mismatched. So you see the equation output is off. Now I have an error. So I go through here and I have to add the parentheses back in. Okay, so I'll add it back and then where are we at? Yeah, brain fart. There it is. So if I add it back, now if we go back to status, so now the equation error is gone. Now still same thing. So say if I mess something up here, and instead of AI1, I made it A11. So hit apply. Go to input. So right here, DO1 equation bad type. So it's saying the equation is a bad type. Now that's because I have a spelling error or a grammatical error. I used a 1 instead of an I. That's why these are super difficult to troubleshoot, guys. Like when you're getting into like 2-line equations where there's multiple parentheses, making sure the parentheses are in the right spot. It may take a little bit of playing with. And the biggest thing I can tell you guys is find a bunch of flexible combiners in the controller, okay? Back the program up and then break them down. So I'll break them down. Like if statements, I'll write them out, okay? I'll write them out on paper. It's pretty easy to write them out on paper and try it. I have been told you could do them in Excel. I've never tried it. I've seen people do it, but you could do all these equations in Excel because Excel does Boolean logic. So you could do these in Excel and do them. But here's the thing, guys: break them down to where they're like written out and what they are, and try to break down the sequence operations and test them. Do change the analog input, change the analog output, to see what it's doing. I mean, this is how you guys can break these down and learn. I do a lot of stuff with flexible combiners because it's easier for me to write the logic, but also I got to watch what I do on them because if I make them too complicated, then somebody's not going to be able to figure them out and they're going to override something or they're just going to write it up and then it makes a bunch of nuisance calls. So, I mean, pick and choose your battles. I don't do everything with flexible combiners, but I do a lot. And we're going to make another episode. We'll go over an advanced flexible combiner episode. So we'll go from there. All right, guys. Thanks for watching, and I appreciate it.